actually really enjoyed it, and I took some notes, and now in the aftermath, I'm having to remember, okay, who was it we talked about that with? But I shouldn't have disclosed that right now. You have no confidence in the grading process. No, as I talked with each of you, I got a very good sense for what it was that you understood, and so that's in a lot of ways way more effective than a written exam. As I wrote in an email earlier today, my point was not to identify all the mistakes you were making, but to get a sense for your overall understanding. So you don't need to worry if you feel like we left something out about your question because we didn't have enough time. I was just trying to have a discussion with you. And honestly, it could have been shorter. After about 15 minutes, I could get a sense for where you were. So in any case, I enjoyed it. I hope it was useful. I'm not sure we'll do the rest of them that way. We'll just sort of have to see. If you absolutely hate it and never wish to do it again, that might be interesting to know. Maybe we'll do an awful written exam and then you can pick which one you want, right? Okay. Well, today we're talking about conformations, which is kind of a fun topic in organic chemistry. This is going to come up again and again in reactions and in shapes of molecules. This is a topic near and dear to me because I'm interested in protein and peptide folding, and all that is rotation around bonds. So we'll start pretty simple and move on from there. I've got lots of figures here that are from the text. I'm sorry about that. I typically like to draw things out while we're talking, but some of the drawings are complicated enough that I figured it wasn't necessarily worth our time to try to reproduce it. But they'll be in these notes, and you've got the text, so you'll have access to it. I guess I don't want to say too much about ethane and butane conformations, since that's kind of a topic from sophomore organic. One of the things, just to facilitate our discussion, though, today is the definition of a dihedral angle. It has a more technical definition than this, but if you're looking down a carbon-carbon or any kind of bond, and you choose a group on the front and a group on the back, and then measure that angle between them as though the whole thing was flat, that's called a dihedral angle. Now, the technical definition of a dihedral angle is it's the angle between two planes or the angle between two vectors. So if you define this as a vector and then this to the carbon in the back as another vector, you can identify their dihedral angle. The angle between two vectors is related to the cross product. So, dot product. Yes, it's the dot. Anyway, maths can give you the dihedral angle. So if you're ever dealing with 3D coordinates, XYZ coordinates for molecules, it's very easy to write. A lot of programs will let you pick the atoms, and it will tell you what the dihedral angle is, but if you want to do it yourself, it's really trivial. You just have to look up the formula. Interesting feature here is that the barrier to rotation in ethane is about 3 kilocalories per mole. Now, in terms of equilibrium constant, that's huge. In terms of the thermal energy that's available at room temperature, that's not so huge. So your text tells you if you want to know about how much thermal energy you have in an ensemble of molecules at room temperature per mole, then you just calculate RT, which is the gas constant times temperature. And at around 298 Kelvin, I believe your text says RT comes out to be about 0.6 kilocalories per mole. So if this is 1 and this is 2, that means that on average, a lot of our molecules are sitting at, the overall ensemble of molecules has about that much energy. But remember that molecules at room temperature are bumping into each other very rapidly, and it's not like they all have the average temperature. You've got a distribution, which if you took PChem, you might know something about that. There's a Boltzmann name, it's a Boltzmann distribution. I don't know. But basically there is enough thermal energy as molecules bump into each other to populate the quantized energy states that exist. And when you get close to the top of a barrier, the difference in energy between those quantized states drops to zero, and you basically have a continuum. And then you get free rotation. So it's actually very easy at room temperature to rotate around that single bond, which we all know. And if you don't believe me, then we can go to this fun play with wiggling molecules. These are real live molecular dynamics simulations, and they glow, which is kind of cool. I forget whether ethane, ethylene, ethyl, THA. Hey, there we are. Hey, so, and right now we've got a bath temperature of about 50 K. But we wanted to be around, wouldn't it be nice to change temperature that fast? Our hot water heater busted a thermocouple and the pilot light went out. Yesterday morning, we took my morning shower and it was tepid because fortunately water has a high heat capacity, so it takes a long time to get cold. But this morning it was freezing, and it was a not good experience. I don't know why I'm telling you that. Okay, now you can see that we're at 290-ish, 298-ish. I can't get quite to 298 room temperature. This is just one molecule, but it's sort of the internal energy you would expect if it were bumping into solvent molecules. You can see this individual molecules internal energy bouncing around. Sometimes it's higher, sometimes it's lower, and over time, if you watch, and we sort of try to, it's hard now. Did you see it rotate? Okay. So that happens easily at room temperature. Of course, if you want to cool it down, you can freeze out certain conformations. Here's an interesting idea at temperatures that are really low where rotation isn't possible. Suddenly, do you have a molecule that's chiral or not? Maybe. Anyway, interesting thoughts to think about. Yeah, Dakota.
That's considered chiral even though 3 groups on the carbon is the same?
No, but there are ways to freeze out in more complicated molecules. If you remember learning, I think in your OChem lab about enantiotopic versus homotopic protons, we'll talk about that when we get to stereochemistry. But at low temperature, I think you can start to tell enantiotopic protons apart. Maybe I'm making that up, but we'll see.
Also, based on this graphic, it looks like even at room temperature, rotations are pretty infrequent, but they happen frequently enough at least that you can't.
Well, I don't know. I mean, that's a good question, and I don't know how realistic this is.
Like, it's not constantly rotating around through the eclipse.
Yeah, but it's fast enough that you don't see, at least on the NMR timescale, which your text talks about, you don't see more than one kind of proton in ethane. So, however, oh, that's the problem. We're looking at this in a femtosecond scale. So you're still looking at 300 femtoseconds per 1 of our seconds. So you got to speed that up by 10 to the 12, and then you could see how rotation would be free.
Yeah, it looks like even so, the molecule sometimes struggles to rotate.
Yep, and that's because of what we talked about here. You have a barrier there, and not all the molecules can surmount that barrier. But let's see, 10 to the 12 seconds, how long is that in years? How long would we have to wait and stare at that to have 1 second pass in our time?
That's about 32,000 years.
Okay, so on that time scale of 1 second, yes, there would be free rotation. All right. It gets a little more complicated when you get to butane, of course, because if you look at rotation around the central carbon-carbon bond, whoops, I wanted to say something else. Most texts will tell you that this is a steric hindrance. There is a counter argument, and that is that there is better hyperconjugation between a bonding orbital in the front and an anti-bonding orbital in the back when it's staggered. And we don't need to make too big of a deal of that. You may have learned about that in 351, but that's an alternative explanation for this 3K cal per mole barrier. Yeah.
Yeah. This is not this type of rotational barrier, but in 465 we did a lab dealing with NMR and amide rotation.
Uh-huh.
And with that, 70 degrees Celsius was about the critical temperature.
Really?
At which
Okay.
they converged.
Yeah, that's a good point. Some of these things are temperature dependent, and your text has a going deeper highlight that actually talks about the relationship between temperature and conformational processes and how you can expect to, whether or not you can expect to see two different signals on the NMR timescale. And we'll probably come back to that as we talk about non-covalent interactions. All right, in butane you've got the two methyl groups, so there are a few different staggered conformations. You have the anti one, where the methyl groups are opposite each other, and that's the global energy minimum. And then just about a kcal per mole above that, you have the gauche conformation, where the dihedral angle between those methyl groups is around 60 degrees. I don't know why we're writing in pink, but it's okay. Yes? Oh, I always do that. Thank you. All right. Sorry about that. We'll see that technically you can distinguish one gauche conformation from another. And what do we need but more nomenclature? On the right here, on the left, it's just showing you how a dihedral angle is the angle between two planes. It's not that important. On the right, it shows how people talk about dihedral angles. Of course, if you're on the same side of the molecule as the group in the back, that's syn. If you're on the opposite side, that's anti. That should sort of be familiar. Here's a term that you've talked about before, I think, because in 351 or 2, we talked about elimination requiring an anti-periplanar arrangement of beta proton and leaving group. Periplanar means in the same plane. Anti tells you it's opposite. You could be syn periplanar, but anti-periplanar. And then if you're between like 60 and a dihedral angle of 60 to 120 degrees, you're in this clinal region. So if you were on this side of it, it would be synclinal. It could be anticlinal. Alternatively, on the right side, people call that minus, and on the left side, they call it plus. So if you were over here in gauche, it would be minus gauche. If you were over here in gauche, it would be plus gauche. So with our group in the back, it looks like, as the reference point, this is a gauche plus conformation, and then over here would be the gauche minus conformation. And the gauche minus conformation and the gauche plus conformation are actually enantiomers of each other, though they interconvert so rapidly that we say that this molecule is not chiral, except it's not even the same molecule there. Sorry about that. Okay, another thing to think about here is just the barriers you have to surmount to rotation. A hydrogen-hydrogen eclipsed interaction is a barrier, well, 3 of them, so each one is a barrier of about a kcal per mole. A hydrogen methyl gauche interaction costs more, right? If it were just all hydrogens, it would be 3 kcals per mole. It's a little bit more to go from anti over to gauche, okay? And then to go from gauche plus to gauche minus through the eclipsed methyl conformation is an even higher energy penalty. So what this means actually is it's way more common to interconvert gauche conformations by going through the anti-conformation instead of converting directly, because that barrier is higher to get over. Yeah?
Because the in this case, the fully eclipsed conformation is very unfavorable. So
That's
it's
right.
easier to go around
Yep. When the two methyl groups are eclipsed with each other, you get steric repulsion, electron-electron repulsion between the methyl groups. Okay? So, I don't know. Maybe we beat that one to death, but anything we need to add there? So it turns out you can, based on the data that they have obtained, you can start to add corrections to calculated heats of formation. As an example, your text asks you to look at the difference between 2-methylpentane and 3-methylpentane. And if you calculate heat of formation based on group increments like we did last time, you come up with a strain-free estimate. But reality is that these molecules are not that stable, and you can calculate based on, if you didn't account for strain, you would say, oh, these two molecules are equal in stability. If you look down this carbon-carbon bond in the front, you would see, and we're not going to draw all the possible conformations, but there is the possibility for an ethyl group to be gauche to two different carbons, right? Because this carbon is disubstituted. I don't know actually what we're... I don't think I actually want to go through this analysis. I thought about it, but it's not totally clear to me how to count all the gauche interactions, and I'm not sure that'll be important for us, other than to say that each gauche alkyl type interaction is worth about a kcal per mole in stability. So consider that. That's sort of the penalty for having groups gauche to each other. Anything else you want to say about that? So one question we can ask is, if you've got the choice between gauche and anti, is gauche always bad? And this is where we pull back the curtain and make life a little more complicated for you. So back in the 90s, Professor Ron Raines at the University of Wisconsin-Madison was interested in collagen, and actually his interest in collagen continues to this day. He's now at MIT. Collagen is a peptide that's slash protein that's it exists in a triple helix. It's a structural protein, and so problems with collagen can result in bone issues and other tissue types of issues. One of the interesting things about collagen is it's mostly the amino acid proline. It consists generally of a repeating sequence of amino acids, a proline, another proline, and then a glycine. And sometimes the proline in the middle has a hydroxy group added post-translationally on carbon number 4. So this is an example. This is just a regular proline amino acid. It's got an acetylated amino group and then the methyl ester on the acid. So this is just a model compound. This is 4-hydroxyproline, and I'm not telling you what the RS configuration is there because I didn't figure it out. It's known, but this OH is down. And it's this one that's found at that second position in the repeating collagen sequence. And it's known that that residue, that hydroxyproline, is actually important for collagen structures. There are conditions that are related to hydroxyproline deficiency if your body can't make hydroxyproline. And so they've been interested in understanding what the deal is there. A hypothesis had been that, well, it's an OH group, therefore it must be hydrogen bonding with something, and maybe that stabilizes the triple helix. But they weren't sure. And so they did some experiments where they replaced that OH group on carbon 4 with a fluorine, which is more electronegative but lacks hydrogen bond donating ability. Now, they crystallized these compounds, and one of the interesting things they noted, they sort of wanted to see, do these groups influence the conformations of proline? So, here is a representation that I drew of what they said they found in the crystal structure for this particular proline derivative that doesn't have an electronegative group on carbon 4. And we'll talk more about ring conformations. Here is a 5-membered ring. It's not a cyclopentane because it's got a nitrogen in it. It's called a pyrrolidine. Yes? Help me? No? Pyrrolidine, I think, vaguely. We can look it up. I think a 5-membered ring saturated that contains nitrogen is a pyrrolidine. The fully saturated aromatic compound is pyrrole, so that makes sense. Okay, sorry, that's an aside. Of course, the 5-membered ring to relieve angle strain is not completely flat, it's puckered. We'll talk more about that, but this is called the C-gamma endopucker because the carbon adjacent to the carbonyl group is alpha, then beta, then gamma, and it's called an endopucker because when you look at it from this direction, that C gamma is up, sort of out of the plane of the other 4. And we're not going to require, I'm not going to require you to name conformations of 5-membered rings. You should be aware that they pucker, that there's a couple of them that they can adopt, and know that sometimes they're important, but when you get confused, you will do what I did this morning, which is just look it up, and then you'll know. But know that it's a thing. In contrast, they found that when you put the hydroxy group on the gamma carbon, the conformation is instead a C-gamma exo conformation, where C-gamma is now angled down relative to the other 4 members of the ring. So up, down. Okay. Why is it called a pucker? I don't know. Does it look like puckering lips? It does not. But a pucker in your clothing? Okay. All right. I went immediately to the kissing, but sorry, but that may okay, a little pucker and a fold, or whatever. And then in the fluoro derivative, they also found this C-gamma endopucker. A related issue that we won't talk about, but it gets to one of Dakota's earlier questions, is that there were different conformations preferred about the nitrogen-carbon bond here. In the proline case, the cis amide was preferred, where the alpha carbon here was on the same side of the amide bond as the alpha carbon here. In contrast, if you use the OH group or the fluorine group in this stereochemical configuration at the gamma carbon, you favor the trans amide. And this was in early days, and they thought this had something to do with the electronegativity of the oxygen and fluorine atoms, and it probably does. But there's something else actually going on with these, with the oxygen and with actually the pi system of this ester that we'll talk about, I think, when we get to the non-covalent interactions chapter. And it's thought that the C-gamma exopucker actually facilitates an interaction between this oxygen and this carbon. So that's just an aside. But I want to point out, if we just look at the hydroxyproline, and let's put ourselves, this is going to be weird, we're going to put ourselves in back of the C-gamma carbon, and we're going to be looking down the bond between C-gamma and C-delta. So here is our eyeball looking down that bond, and we are Anakin Skywalker in his evil phase. Okay. And so put yourself back there and let's imagine what we would see. If we were back there, the hydrogen would be coming out to our right, the OH group would be going down, and then to our left would be the beta carbon. In back, on the delta carbon, we'd have a proton going up to our, oh dear, up. Another proton going up to our, out to our right. Am I getting that right? And then the proline amide nitrogen out to our left. So take a minute and look at that and see whether I've got that. I mean, it's easy. Just come back here and look through. All right, so if I'm behind the board, I'd see that hydrogen on the gamma carbon out to my left, the oxygen here, and the beta carbon there. And then at the carbon in back of me, you've got the proton up, the other proton angling down to my right, and then the nitrogen out in that direction. All right. This is the preferred conformation that they found this molecule adopts in the crystal structure. And interestingly enough, the OH and the nitrogen are gauche to each other. All right. Now, it's also true that the nitrogen is gauche to the beta carbon of the ring. It has to be. It's a ring, right? But that's not the only option. If we look at the C-gamma endopucker, where the OH group is not in a sort of down axial, but is in a down pseudo-equatorial conformation. Holy Toledo, what have I done here? Holy Toledo, where did I pick that up? From my father-in-law, who I think picked it up from Batman cartoons. Or no, the old 1960s Batman. Anyway, sliding down that bond again, got the same sort of stereochemical relationships. In front is our gamma carbon. OH would be down to our right, proton would be up, beta carbon would be down to our left. Then in the back, what have we got? Hydrogen, hydrogen, and nitrogen. So now the OH group is anti to our nitrogen of the proline ring. Now, if this were 351 and we didn't know anything else about this molecule, we would probably conclude, well, gee, there's no way that the nitrogen can ever be anti to the ring. Oops, I wanted a pointer there and I got a marker. The ring carbon, the beta carbon, that's just not an option. But if you have a choice for it to be anti to the OH group or gauche to the OH group, we would choose anti every time, right? Go ahead.
The only reason gauche could possibly be more favored is if hydrogen bonding from the H to the N is...
So that is a good question. Could there be hydrogen bonding from the H to the N? I think that's reasonable, and there's if this were some if there were some other atom here, like an OH group, that might be a consideration. It turns out the lone pairs of that proline nitrogen are not that available for hydrogen bonding because it's an amide proton, or it's an amide nitrogen. In any case, the gauche one is actually preferred, but that preference goes away when you get rid of the OH group. So it's not hydrogen bonding. What the heck is it? Well, let's simplify the situation a little bit, and we could do the same for the fluoroproline derivative. But let's just do 1,2-difluoroethane. Okay? Two atoms with a heteroatom, two carbons with a heteroatom on either side. That is going to be analogous to our bond between gamma and delta carbons. All right? And it's known in such cases when you have 1,2 heteroatom substituents that the more favored conformation is to have the fluoro groups gauche to each other. Okay, so this is true even if the groups get a little bit bigger. Fluorine's pretty small, so you might say, okay, the penalty for being gauche isn't that bad. But this is true even if one was OH and one was fluorine. If it's not sterics, it's probably electronics. So what's going on here? And the answer happens to be, like most answers in 351 and 352, hyperconjugation. All right, so let's consider we're going to take a hybrid valence bond theory, MO theory approach, where we're going to consider bonds localized between atoms, but we're going to remember that antibonding orbitals exist. And you can do that, and you can get answers that are fully equivalent to what you would get through MO theory. It's called natural bond order analysis, and it's a little box you can check in Gaussian that'll actually give you orbitals that seem to correspond to specific bonds a little bit more. In any case, the carbon fluorine sigma star would have a node here, and then we'd show it having a lot of electron density there, some here, and some there. That's sort of a crude imitation of what a sigma star for fluorine might be expected to look like. Ooh, I changed colors. We're no longer pink and yellow. We're purple and orange. Fun. It's because it's October. We need to get some green in there, and then we got some Halloween colors. So notice that when the fluoros are gauche to each other, the carbon fluorine sigma star on each carbon gets to overlap with a carbon hydrogen sigma in the back. And that's better than overlapping with a carbon fluoride sigma. Can you explain or justify why it's better, more stabilizing for a carbon hydrogen sigma to overlap with this sigma star than for a carbon fluoride sigma? Yeah, go ahead, Kim.
I mean, I would assume that the carbon hydrogen sigma is lower in energy, and so you're going to net be more in energy when it overlaps with the carbon hydrogen than with the carbon fluorine.
Okay, so you're saying that you expect the carbon hydrogen bond to be lower in energy than the carbon fluorine bond. Okay. Who knows rule number, what is it? Rule number electronegativity in our QMOT approach. Fluorine's electronegative, and orbitals that are on more electronegative atoms are therefore lower in energy. So the carbon fluorine sigma bond should be lower in energy than the carbon hydrogen sigma bond, making the carbon hydrogen bond a better donor for that sigma star. Yep. So, right, we've said due to fluorine's electronegativity, carbon hydrogen sigma a better hyperconjugative donor than a carbon fluorine sigma. Okay, and this is actually, this thing has a name, this effect, this observation has a name, and you can go look it up on Wikipedia. It's called the Gauche Effect. And it's observed a lot when you have heteroatoms on adjacent carbons. Yeah?
So I understand why the carbon hydrogen bond would be more likely to hyperconjugate with the antibonding orbital. But
Yeah.
why is that better? Why is that a favorable thing? The antibonding orbital.
Good. Let's talk about that. So we're going to do a crude orbital mixing diagram where I'm going to show the carbon fluorine sigma star and over here the carbon hydrogen sigma in the same molecule. So we're basically doing group orbitals, only we're talking about single bonds, or we're going to think about mixing these two orbitals together. A related way of thinking about this would be, actually I haven't thought about it from a QMOT approach, so whatever. From a hyperconjugation point of view, though, if you mix the carbon-hydrogen sigma with the carbon-fluorine sigma star, the electrons in the carbon-hydrogen sigma get to move lower in energy. The carbon-fluorine sigma star, which was empty anyway and doesn't count in terms of the stability of the molecule because there's no electrons, goes up in energy.
And Josh, wouldn't
Yeah.
it be true that if it was with the carbon fluorine, like we wouldn't get as much stability because the delta would be bigger? Or?
Exactly. So if carbon fluorine is down here, remember that the gap between orbitals determines how much the new bonding orbital goes down in energy. And if the carbon fluorine bond is lower than the carbon hydrogen bond, the mixing with the sigma star is not going to be as effective. Yeah.
And this is probably a question that students would have asked in 351, but why is hyperconjugation hyper? Is it like a more super version of regular conjugation?
So yeah, it's a good question. The question is, why is hyperconjugation hyper? Is it different from conjugation? I might be wrong on this. I've heard Dan S. explain it before, and I think I wasn't listening carefully enough. My understanding is that hyperconjugation is originally a valence bond theory, and I'm just going to, a valence bond theory concept, which says that these no bond resonance structures are important. And I think because they involve no bonds where sigma bonds used to be, instead of conjugation, we call it hyper conjugation.
It's called hyper because we're going all the way to no bonds instead of regular conjugation, which is single level, single double.
That's my hand wavy explanation. So sorry. Conjugation specifically is an extended delocalized pi system due to a cyclic and aligned array of p orbitals on adjacent carbons. Hyperconjugation is mixing of an empty orbital with a filled orbital in the same molecule. So related concepts, but yeah, I don't exactly know the precise reason why it's hyper. Yeah, go ahead, Jared.
So just kind of a follow up on the why hyperconjugation even happens. So usually, like, we would talk about it as a thing that happens in carbocation.
Uh-huh.
And like I always kind of understood it as, well, the carbon that's electron poor, it wants electrons, so then the adjacent groups don't need electrons.
Right.
But is the real motivating factor actually that those electrons get to go down in energy, and it has nothing to do with carbon that's electron poor? It's just a way to go?
I think that's a great question. The question is, and I'm repeating this for our audience at large because the mic doesn't necessarily pick up the sound. The question is, hyperconjugation made sense in terms of carbocations because you're donating electron density into a positive charge, but is the real explanation that the electrons in the bond that is donating get to move down in energy? Yes, I think so. Yeah. And in my mind, again, if you did the full-on MO approach, you don't need hyperconjugation or even resonance because all the electrons are delocalized. You have molecule-wide orbitals. And since you're no longer focused on individual bonds, all you would say, and we could try the QMOT approach with this 1,2-difluoroethane, you would conclude that this arrangement gives you overall lower energy than the other arrangements. That's difficult to do as the molecules get more complicated, and the valence bond theory focuses on bonds, which we can draw in our Lewis structures, but it's inadequate unless you build in resonance and hyperconjugation. If you think of those things, then you get basically to where the MO picture was going to get you. Yeah. All right.
So Josh,
Yes.
so you talked about how people talk about human projections and stuff. They're like, it could be sterics, it could be hyperconjugation. This is showing like hyperconjugation being the explanation.
Uh-huh.
Is there any way you can predict when the Gauche effect will be taking primary?
Okay, good. Well, you make a prediction. Do you expect the Gauche effect to be more important for fluorine or for oxygen?
I mean, I would assume.
Because basically the Gauche effect is related to that energy gap, right?
So, I mean, fluorine's more electronegative, so
Uh-huh.
more.
So it should be a little weaker for oxygen, and then and so on. And Rains has done some other things with other substituents at carbon 4. I think they've compared chloro versus fluoro. I can't remember what they saw. And there you've got multiple issues because carbon chlorine bonds are longer than carbon fluorine bonds. And so there's multiple things at play here. But yes, if the issue is that bonds between carbon and electronegative heteroatoms are low enough in energy that they're not great hyperconjugation donors, then yeah, you've got a trade-off between sterics and hyperconjugation, and the more electronegative your atoms are, the more likely the sterics are to win. It also helps that fluorine's really small. Cool. Others? So another sort of trivial, and you can forget it, I didn't, case is where gauche is not bad, is in a 1122 tetra-alkyl substituted ethane, where the carbon in the front and the carbon in the back both have alkyl groups. Okay, so here is an anti-conformation. You do have a gauche relationship, but you've got as many anti-conformations as possible. And what is observed in this situation, even though you've got methyl groups that are anti to each other, and you've got the most anti groups as possible, there is actually steric repulsion between the methyl groups on the same carbon. That's called geminal repulsion, because they're on the geminal is a word we use for the same carbon. It's derived from, I think, the Greek for twins, Gemini, right? And then vicinal is for neighboring carbons. Vicinal is the word from a root for neighbor. Spanish vecino, right? Is that neighbor?
Yeah.
Yeah. My Spanish is really bad Tex-Mex from 20 years ago. So, anyway, the geminal methyls will tend to widen their angle to get away from each other. We saw actually some of this on the exam. And that will have the effect of pushing the gauche interactions closer, ironically. In contrast, if you are in an all gauche conformation where the methyl groups are all gauche to each other, geminal repulsion tends to ease things up a little bit. So it's a minor issue. Your text mentions it. I thought I'd mention it just as another example of sometimes gauche isn't bad. Now, as you start to go beyond butane, things get a little complicated. So here is pentane, and it has basically 3 unique conformations. You've got a conformation where, and let's be clear, I'm naming these conformations according to a 2-letter convention. We're talking about rotation around these 2 bonds, okay? We don't care about rotation around this bond because all the 3 things on that terminal methyl group are the same. So it's going to be in a staggered conformation, and all the staggered conformations there are the same about that bond between carbons 1 and 2. Similarly, between 4 and 5, we don't care. There's only one unique conformation about that bond because all the staggered conformations are identical. However, In the bond between 2 and 3, you have to worry about the arrangement of the methyl group with this alkyl group. And similarly, for the bond between 3 and 4, you have to worry about the arrangement of this group relative to that group. Okay? So the TT designation indicates that we've got an anti arrangement, and you sort of have to put yourself in the plane of the page and put your Sith eyes here and look down, and you'd see that this is anti to that one. Similarly, this is anti to that. So both of those two bonds have anti-conformations. That's probably the most stable conformation, the all-trans version. This one is called gauche minus, gauche minus. Now remember, minus is when we're gauche, but on the right-hand side. This is difficult to see because you can't move this molecule around. So we're going to go to Spartan, which has this lovely feature where we can draw a molecule, and if it has the information available, it's going to give us conformation. So there's pentane, and it's nice, and it has drawn us the all-trans version, and this is the low energy conformation, as you see with the red line at the bottom. Okay, we go to the next highest one, and it is one is gauche and one is anti. This is the gauche one, and then about that bond it's anti. Next is the gauche minus conformation. So how are we going to do this? We want, and frankly, this might be gauche plus, and that's okay. That's the same thing as gauche minus, if that's okay. All right. So about the bond between 2 and 3, methyl group in the front is gauche to the ethyl group in the back. I think based on the convention we talked about, we would call this gauche plus, because if you imagine this at the top, then this methyl group's on the right-hand side. Spartan doesn't make it easy for me to rotate things. Then if we go look down the carbon-carbon bond, again, the ethyl group in front is to the left, or counterclockwise, from the methyl group in the back. So that's gauche plus. That conformation's not as good as anti, because in the anti conformation, everything is all anti. But not only that, is that as you go to gauche plus, you bring, you see, I don't have a pointer in Spartan, so I'll have to use, there's just no way. So I will just, this proton here on carbon 2 sticking out is decently close to this proton on the methyl group over there on carbon 5. Yeah.
Yeah. The gauche minus, then gauche plus, you can think of as an almost cyclo conformation.
Uh-huh.
Where the two ends
Yeah.
together.
Yeah, that's interesting. When you start to mix opposite sign rotations, you actually start to get something like you're rotating around to the same spot. And that is precisely why the gauche plus, gauche minus, let's see. All right, now the conformation about 2 and 3 is gauche minus, but the conformation about 3 and 4 is gauche plus. So the minus plus conformation creates a situation where, yeah, now methyl groups on 1 and 5 are actually getting close to each other. You can see the molecules sort of distorted, and some of the bond angles are in order to prevent those two methyl groups from bumping into each other. But that conformation, that's a fairly destabilizing effect, and it's long range, right? If you look at this, it's obvious that the all anti conformation is the best. What might not be obvious is that all the gauche conformations are not equal. And there's a few of them that are about the same. There's a couple of them that are about the same within 1.5 kcals per mole of the all anti conformation. But it requires 3.7 kcals per mole to get to the gauche plus, gauche minus conformation. You can think of that as a molecule in order to get to that conformation, a mole of molecules in order to get to that conformation would need to absorb 3.7 kcals per mole from the surrounding molecules of kinetic energy from the surrounding molecules and store it in this much potential energy. And it's stored as torsional strain. All right. This introduces actually a really important concept in chemical biology and physical or organic chemistry. Because if you look at this Gauche plus, Gauche minus conformation, and imagine making a bond between carbon 1 and carbon 2, you've already mostly made a 5-membered ring, right? But in a 5-membered ring, the all anti conformation isn't an option, so you've basically already paid to get here. And you don't have to pay for it in further future processes. And we'll see in organic chemistry that if you can pre-organize things to the way they need to be to make a process happen, you will make that process more favorable because you don't have to pay for all of that strain. You did, but you did it earlier. All right, so we're out of time. That didn't go quite as fast as I'd hoped it did, but we will proceed. I imagine we'll need 1 to 2 more lectures on Chapter 2. I have not yet posted a study guide for Chapter 2. I will do so. Exam scores you can expect either later today or Monday. With that, have a great weekend, and I will see you next time.